In this lecture, we'll explore two key questions. One, how is electron configuration related to the arrangement of the elements in the periodic table? And two, how are periodic trends determined by electron configuration? In our previous lecture, we learned that an electron's location can be defined by a principal quantum number, the subshell in which the electron resides, and the orbital that resides within the subshell. The orbital is kind of like a house in which an electron lives, and each orbital exists within a subshell, which you can think of as being a street, and the principal quantum number, which you can think of as being like the city. The principal quantum numbers that we have for electron shells are also called electron shells, and they come from n equals 1 to n equals 7, and they correspond to rings in a Bohr model, with n equals 1 being the smallest ring and n equals 7 being the largest. So the four types of subshells are S, P, D, and F, and they have each subshell has more lobes than the last. The S subshell only has one, so it's like a sphere. P has two, so it's like a dumbbell, and then D and F have more lobes in a more complicated shape. So because they have this more lobes and a more complicated shape, they can hold more electrons. And they have more orbitals. So the S subshell has one orbital, the P subshell has 3, the D subshell has 5, and the F subshell has 7. Now recall that an orbital always holds 2 electrons, so that means that S, P, D, and F hold 2, 6, 10, and 14 electrons total. Orbitals fill from the lowest energy to the highest, so it's kind of like, imagine like a ball, like if it's on a hill, it's going to go to the bottom of the hill. It's the same thing with electrons. They go to the lowest energy orbital that they can. So the very lowest energy orbital that we have is in the N subshell, and that there's only one subshell here, the S subshell. So 2 electrons can reside there. Then we move up to shell 2, which has 2 subshells, S and P. S can hold 2 electrons, P 6. Then we move up to 3, which has S, P, and D. And we have 2 electrons in the S subshell, 6 in P, and then D can hold up to 10. And then in the 4th shell, we have S, P, D, and F, and we have S holding 2 again, P also holding 6 again, D holding 10 again, and F holding 14. And then once we get up to the larger shells, there's no more subshells, so 5, 6, and 7 also have S, P, D, and F subshells, but we're not going to really talk about those in this course. You don't have to worry about it. Now, electrons fill in from the lowest energy to the highest energy, and you can figure out what that is by looking at this crazy little table, either in your book or in your periodic table handout. And so, for example, carbon has 6 electrons. So looking at that, the S subshell is going to fill 2 first, so that's 1s2. 2 electrons go there. Then we're going to jump up to the 2s subshell, which is the next highest, so 2 electrons there, and then that's 4 electrons. We have 2 left to account for, so that's 2p2, so that's 2 in the p subshell, and at that point we've accounted for all of the electrons for carbon. All right, so we learned the electron configuration, and we also learned some things about the periodic table, and in this lecture we're kind of put the two together. So let's quickly review the information that we learned about the periodic table, in particular that it's divided into blocks. And a block indicates which orbital is filling. So on the left-hand side here of the periodic table, the first, group 1 and 2, the S subshell is filling. So these are main group metals. And then after that, the orange elements that are kind of like low down in the table, that's the D block. And in the D block, so obviously that means that the D shell is filling. Then to the right of that, we have more main group elements. We have the nonmetals and metalloids, and these pink ones, the P shell is filling. And just look at helium is like a little bit different because it's in row 1, and that only has a row 1 or period 1. There's only in the n equals 1 shell, there's only an S subshell. So for helium, S is filling, but for all of the other elements in that group, we have the P subshell is filling, or in this case full, because these are noble gases. And then we also have at the bottom the lanthanides and actinides. Now remember that the periodic table, they actually fit in between the groups 3b and 4b of the D block elements or transition metals. For the lanthanides and actinides, the F shell is filling. Okay, so the blocks of the periodic table tell us what subshell is filling, but we can also find other important information by looking at the groups and periods of the periodic table. Now remember, a group is a column going down, and a period is a row going across. The group number tells us how many electrons are in the valence shell, at least for the main group elements, which are the ones that have the taller columns. They're labeled numbers here, 1, 2, 3, 4, 5, 6, 7, and 8. For these groups, the group number indicates how many electrons are in the valence shell. So group 1 has 1 valence electron, group 2 has 2 valence electrons, group 3 has 3 valence electrons, and so on. The period indicates which shell is filling. So there's 7 rows, and so going down the table, we have group shell 1, 2, 3, 4, 5, 6, or 7 filling. Now remember, the lanthanides and actinides that are in the gray at the bottom, they actually belong, the lanthanides, the top one of these gray columns, belongs in row 6, and the actinides belong in row 7. So the lanthanides have shell 6 filling, and the actinides have shell 7 filling, and there's no larger elements, at least that we know of as of now, that have larger, that have shells beyond 7. We also, in our previous lecture, learned about valence electrons, which are the electrons in the outermost shell. And the shell itself is called the valence shell. Valence electrons are important because they're involved in chemical bonding. Now, the reason that valence electrons react is because the outermost shell is often only partly filled, and it's like a wheel out of balance. It's unstable, and it tends to want to gain or lose electrons to achieve a completely full or completely empty shell. Now, all of the electrons that are not valence electrons are called core electrons. Core electrons do not react because the core shells are always completely full, and they're stable, so they don't want to gain or lose electrons. And the image in the bottom here shows the core and valence electrons of carbon. So carbon has just, it's in period 2, so it has 2 electron shells. The outermost shell is shell 2, and the valence electrons are shown in red. Shell 1 is core electrons, which are completely full. The valence shell only has 2 electrons in the P subshell, and remember the P subshell can hold 6 electrons total, so it's partly full, and this is an unstable situation, so carbon tends to react so that it can achieve a full P shell. Just one other thing I wanted to mention about valence electrons, or review about them, is that the valence electrons are the ones in the outermost shell, even if the shells fill out of order. Now, recall that the S subshell has slightly lower energy than the D subshell, so this is only an issue when we get up to the fourth shell, because before that we don't have a d subshell. Now in the fourth shell, we have the 4s2 fills before 3d10, but if we look at selenium here, the valence electrons are in shell 4, so you look at the number, and it's the highest number shell that contains the valence electrons. Now we'll take a look at the noble gases, which are on the far right column or group of the periodic table. Recall that the noble gases have a completely filled outermost or valence shell. So because the shell is completely full, these elements are non-reactive. They don't want to gain or lose electrons, so they tend not to form compounds. Other elements strive to achieve an electron configuration that's the same as that of a close by noble gas. And for this reason, the electron configurations of noble gases are called the noble gas configuration, and it's what elements want to achieve. For all of the noble gases larger than helium, the configuration is S2P6. Now the shell depends on which element you're talking about, which noble gas. But there's two, in each case, there's 2 electrons in the S subshell and 6 in the P subshell. Add that together, 2 plus 6 equals 8. 8 electrons. Since 2 electrons in the S subshell and 6 in the P shell give rise to a total of 8 electrons, for a full shell, 8 is a magic number, which gives us the octet rule. According to the octet rule, atoms of all elements strive to have the highest shell filled, or the valence shell filled, with a complete set of S and P electrons, 8 of them in total. They will share, give away, or gain electrons to achieve an octet. When the electrons are evenly distributed around the nucleus, it leads to a stable, balanced electron configuration, kind of like these 2 people on a seesaw. When both of them are on there, the seesaw is balanced. If one of them got off, it would fall to one direction or the other. Now, when we have a full electron configuration, that is the most stable, and it leads to the lowest energy possible. So, as we've emphasized throughout, electrons want to be in the lowest energy state possible. And to do this, they first of all exist in the lowest energy shell possible, but they will also react to get into a lower energy state.